We're sticking to our guns. We've got a chance to make a difference in this life. But I wonder if you're leading me. And don't you wanna be tired of all these things, scared of living in the past? And don't you wanna be free from all you see, not scared it won't last?
I see this man run. I often wonder why I get a little high every time I see this man run. Man on the run. How far can he go to no one will come? And some will endorse him. If only we found a way to bring and lock him up. He's pedaling backwards, pushing our ways back through this world till we lock him up.
Good afternoon, everyone, and welcome to the third webinar in the series of Future Plymouth 2030. It's Embodied Energy and Whole Life Carbon. My name is Miles Noble from Altitude Design, and I'm here to take you through this afternoon. We have three really great guests with us this afternoon. We've got Simon Sturgis, who's demystifying the operational carbon emissions and embodied carbon. And he's going to explain the importance of the calculation to both provide detailed whole life carbon analysis to inform design decisions. We also have Professor Steve Goodhew from University of Plymouth to present the latest refinements of their new composite earth wall system as a revival of traditional low embodied carbon building method in the modern world. And finally, we have James Robb, who's a senior sustainability consultant at WSP, who's providing examples in the Southwest of how critical understanding of carbon calculation can be used to target and deliver carbon efficient designs. So really great lineup this afternoon. We also have a Q&A session at the end, but if you would like to ask questions throughout the webinar to our panelists, please use the Q&A button at the bottom, or if you feel that you would like to ask your question direct to our panelists, please raise your hand at the end. Without any further ado, I'll send it over to Simon.
I need the host to let me get the screen sharing.
If you just click the green button at the bottom, Simon. Can you see that now? Brilliant.
Great. Well, I hope everybody can see that. Firstly, thank you very much for inviting me to speak today. What I'm going to do is talk you through embodied and whole life carbon as I see it. And what I'll be doing is talking about the sort of, giving you a bit of context to start with, then talk about the sort of what you can do to actually practical steps, and finally some issues on guidance and so on. So the context. So I don't know whether you've seen this pair of graphs. This is looking at 800,000 years worth of temperature and CO2 emissions. And the top graph, the blue line, is CO2 concentration, and the bottom line is Antarctic temperature. And you can see that these two separate lines actually follow each other quite closely, and they sort of rise and fall roughly every 100,000 years. Now, the disturbing bit is to the right-hand side at the very top there, top right-hand corner. You can see that what's happened to carbon emissions is that they're no longer following that sort of rough cycle, but they have jumped right up. In fact, they're above 400 now. When this graph was done, which was only a few months ago, since then it's got worse. So the concern is, of course, and the prediction is that the temperatures are going to follow suit. So that is the sort of basic, if you like, the basic bit behind this. And of course, what that's leading to is things like, this is a photograph in California only a few months ago in the summer of the direct consequence of that, which I'm sure we're familiar with. But the issues really revolve around resource use and the carbon footprint of that. And in a sense, both of those are flip sides of the same coin. If you look at these two diagrams, one on the left is about resources use. So if we all lived like an American, we would need, if the whole planet lived like Americans, we would need 5 planets worth of resources to operate. And you can see on the right there, United States again is the worst. This is per capita CO2 emissions. And without going through these in great detail, you'll notice that fundamentally the same of people are offending, whether it's carbon emissions or some resources. And in fact, the UK sort of, the way we operate is about 3 globes worth of, if everybody was to live like us. So what I'm interested in is, if you like, the carbon emissions from taking resources from the natural environment, turning them into buildings, using them over the life of buildings, and then what happens to them at the end of the life and the carbon emissions associated with all of that. And we're all used to operational emissions, the use of energy, which can generate carbon emissions. But what of course is also very important is the embodied emissions, which come from construction, material fabrication, and maintenance, repair, and replacement, and so on. And very crudely, these are roughly equivalent. They're not exactly the same. In some buildings, one will be much more than others and so on. But they're not massively different, and they're also linked. So activity in one area can produce impacts in the other area. And of course, they will have a direct impact on global warming. So the policy context really dates back to Paris. Well, it actually predates in the UK, but the big one is, of course, Paris 2015. And we in the UK have the Climate Change Act of 2008. We have EU legislation, and we have the UK Low Carbon Transition Plan. And then in 2018, the IPCC, the International Panel on Climate Change, produced a report on what needs to be done to stick to 1.5 degrees. And that then fed into our own Committee on Climate Change, and that led directly to Theresa May's legislation of achieving net zero in 2050. And all of that stuff filters through into guidance, which I'll come to, produced by all these different organizations along the bottom there. But it's also important to consider the investment context, because what is interesting is that the world of money is starting to take a note. And of course, they're worried about it because of risk, and it's going to cost them something. So for example, at the top there, you've got what's called the TCFD, or the Task Force on Climate-related Financial Disclosures. And that organization is chaired by somebody called Michael Bloomberg, who you may have heard of. And this is a subset of something called the Financial Stability Board, which is organized by all the central banks, including the Bank of England. And if you read on the right there, it says the task force's report's widespread adoption will ensure that the effects of climate change become routinely considered in business and investment decisions. And further down, another similar sort of organization says, PRI says, every real estate asset owner and investor must actively manage climate-related risks as a routine component of their business thinking. And what's interesting is that the Bank of England, should be next year, will be starting to stress test big financial institutions on climatic risk. So climate is crawling up the agenda, and you can be sure that people who invest in things, if they're worried about their money, they're going to be worried about climate. They're going to be hopefully putting pressure on people to change their ways. So a bit about methodology. So the understanding of doing an analysis of what the carbon impact of the building is set out in a document on the left there, BSEN 15978. And what that does is it sets out the structure, if you like, which is made up of 4 modules, which I'll come to. And that structure is a sort of internationally accepted way of doing things. In fact, this was copied, well, that's a British standard, copied and pasted from a European standard. The next one along is a similar document, but it's relating specifically to materials and things called environmental product declarations, which increasing number of products will have. It says what it is. And on the right there, you've got a detailed methodology for analyzing, which I led the team as co-author of, Whole Life Carbon Assessment for the Built Environment, published by the RICS as a professional statement. And what this does is sets out in detail how to deliver carbon analysis. And this is being used increasingly widely across the UK. It's people like the European Commission have taken interest and so on. So, mentioned modules. The way we look at it is through 4 modules. And these are A, B, C, D. And module A is the product stage. So what we're interested in there is the raw materials, or indeed recycled material, transport, manufacturing, and then again, after that, you've got the construction stage, which is more transport to the site, and then activity on site. And all of that collectively is referred to as upfront carbon. The next bit, module B, is split into embodied and operational. The embodied in pink is in use, which is to do with things like refrigerant loss and so on, but also maintenance, repair, replacement, importantly. And then below that, you've got operational energy use and operational water use, which is the operational carbon. And the operational energy use, of course, is what we're all much more familiar with in day-to-day energy use in a building. And then on the next one along, module C, is the carbon emissions associated with the end of life. So it's deconstructing a building, the transport, waste processing, and disposal. So that's end of life carbon. And how you demolish a building will set you up for module D to the right there, which is reuse, recovery, and recycling. So the aim of this is that at the design stage, you should be thinking about not just how the building is constructed, the materials you're using, but also the life expectancy of those materials, how they perform over time, how you dismantle the building, and ultimately how you can reuse it and recycle it. And of course, how much energy it uses. So the yellow box represents embodied carbon, and the pale green box around everything is whole life carbon. Although for in arithmetical terms, you don't add D to A, B, and C because it's so far in the future, and although it's useful, it's estimating. So another important point is that carbon emissions occur at different times with embodied operational. So this diagram here is the aggregate of every 5 years. It's the carbon emissions over the life of a building. So in the first on the left there, upfront carbon emissions, you've got the green box, which is the construction of the building. Then the next one along, you've got the beginnings of blue down there, which is operational emissions, and you've got pink, the beginnings of maintenance. And all those pink ones then, of course, are the in-use embodied emissions, repair and replacement. And you can see that up until about 20 or even 30 years in, it's still the embodied emissions from the original construction and indeed some maintenance that are the primary problem. And so if you're looking in the short term, that's the big problem. Obviously, in longer term, it is obviously more important that the operational emissions become increasingly important. And of course, for existing buildings, operational emissions are the prime importance. So getting to zero, how do we get down to zero? So there's a range of things that in practical design sense are the things you would consider in order to reduce the numbers, but also make practical sense. So this first one here, prioritize reuse and retrofit. As much as it says, that's a Victorian building, very durable. And of course, reusing that means you don't have to build a new building, which is of course a very low carbon option. The next one is building efficiency. And of course, this is all about efficient use of materials as much as energy. And building on the right there is clearly a more efficient building. Then this life cycle efficiency. And this is really to do with the choice of materials, but also the life expectancy of materials. So if you take, for example, the building on the right there, those double glazed units will not last longer than about 30, maybe 40 years, at which point they will have to be replaced with a significant embodied cost. So even if they do perform really well, let's say, maybe they're triple glazed units, that they are performing very well in terms of operational energy, they still are a significant embodied carbon problem. Then material is a sort of linear versus circular, and this example is showing anodized aluminium, which because of its nature, it requires a consistent color for the aluminium because the anodizing is a sort of very thin chemical reaction to the surface. And to do that, you have to have virgin aluminium. So it has to come from somewhere like that happens to be in Australia. If you, on the other hand, use powder coating, which is effectively a paint, you can use recycled aluminium. But of course, you also have to consider things like the lifecycle options and so on. But the point I'm making really here is that a seemingly simple choice about something like finish can have a big knock-on impact in carbon emissions. So the linear economy is pretty much what it says. You get a material, you turn it into a product, you use it, and it goes into the bin. A recycling economy is better in the sense that you reuse things, but ultimately it ends up in the bin as well. And a circular economy is obviously idealistic, but it's where everything gets reused and is designed to be reused and nothing ends up being thrown away. Products and construction, MMC, this is modern methods of construction, the ability to make things in a factory, reduces waste, reduces damage, and also the ability on the right there to disassemble buildings is an important part of how buildings may be, or the components may be used in the future. Local sourcing, of course, has short supply lines, less diesel use, but also has social benefits. And this map is illustrating getting something very green, but from Inverness. Is that better or worse than getting something locally sourced, which maybe isn't quite so green? Well, it depends, of course, on the detail, but it makes the point that it's not automatically good to get something, a green product. You need to know where it's come from and how it's got to you. This is really, I think, one, operational and embodied emissions being considered together. So standard insulation on the left there has a certain U value, but also has quite a high embodied carbon cost. The one on the right, natural fiber insulation, may have the same U value, but it has a much lower carbon cost. So really what we should be considering when we choose something like insulation is not just the U value, which is how traditionally we do it, but also the carbon emissions from that product to make it and install it, but also the life expectancy of that product. Because the natural fiber may be great in carbon terms, but if it falls apart or rots within a matter of years, well then you're back to square one again. This example of use of resources, natural ventilation, this is the Everyman Theatre Sterling Prize winner, Hayworth Tompkins Architects. And what they did here was they, on the top, on the roof there, you've got cooling towers built out of brick, and those supplanted mechanical plants. So you had an embodied saving and an operational saving, but you'd have to balance those out and understand how this worked. In terms of cost, this is an example. This was the Google building in London, in King's Cross. And what we found is that every single tender, the lowest carbon option was also the lowest cost, which demonstrated that the image of sustainability being expensive is not necessarily true at all. And this was demonstrated on this. This was a study we did for a developer on a finished building. If you look at those 4 columns, the left hand of those columns shows the as-built carbon emissions. The next one along was what we demonstrated could have been done. And the QS said that that was 75%, those reductions were 75% cost neutral. They were not strange technology or anything, they were perfectly straightforward choices. And those are all, and the other 25% was capable of being tendered, they felt. So this is not an expensive business. This is actually about more efficient use of resources. Life cycle, very important. And this is looking at the replacement cycles of components in that graph on the right, overlaid with in the blue bands, which are lease cycles, to see how efficient the whole life of this building is likely to be. And then overlaid with that is the yellow, which is the sort of an impression of global warming. And can your building be readily adapted in the future? Or is it really complicated to do that? So it's really thinking long term about the life of our buildings. I think we're all familiar with this kind of Victorian terrace house, which I think has probably as many variations as they're possible, probably ad infinitum, but they've proven a really popular and successful, adaptable and durable and flexible building type. So just a brief word on standards and regulations and guidance. If you do a whole life carbon assessment, you also cover a whole range of things like these BREEAM credits and also LEED as well. So for example, but if you carry out a whole life carbon assessment covering the modules A, B, C, and D in accordance with the RICS document, you will more than satisfy MAT 01. In fact, MAT 01 is if you like, a subset of a full whole life carbon assessment. So in terms of guidance, there is, as I mentioned, the RICS document, which is used as increasingly widely, but it's quite technical. If you want something which is more of an easy read, there's the document in the middle, which I wrote, Embodied Whole Life Carbon Assessment for Architects, which is a sort of architect's version, if you like, of the RICS document. It has pictures and so on. So it's much more compatible with, I'm an architect, so I think I can get away with saying much more compatible to architects. The document on the right, the UK GBC's Advancing Net Zero is a good overarching document, and I'd recommend that as well. The last two here, one on the left is the LETI Climate Emergency Design Guide, which does similar sorts of things to the UK GBC design document. But again, it's a really good document, gives you some case studies and so on. And then I'm afraid I'm plugging my book, Targeting Zero, which came out a few years ago now, 2017, but nevertheless it gives you an idea of what's going on. And also it has a number of case studies of all sorts, including from sort of airports to shock horror to things like furniture. So finally, the question is, what do these people want? Because these people are going to be occupying the buildings that we are designing today, and they will have different approaches and attitudes and concerns to those that we have. And I suppose my view is that, if there's a choice over whether new construction should be meeting regulations or should be being ambitious in achieving sustainable objectives, well, I think that my view is that meeting regulations invites relatively early obsolescence, whereas being ambitious is much more about reducing future risk in terms of the performance of your building. And frankly, as we're all working for clients, it reduces the risk of the obsolescence of their building. So thank you very much. That's me done.
Thank you very much, Simon. Really interesting presentation. Thanks for spending your time with us today. Maybe you could post a couple of links in the chat for your book and the easier to read PDF. I think a lot of people would be interested to read that.
Yeah, I'll do that.
We have a couple of polls to go with Simon's presentation. Just the first one. What is discouraging you from whole life carbon assessment? Is it a lack of knowledge and skills? Is it costs? Lack of regulation, the client disinterest, or you're not interested? While you're all voting on that as well, if you missed last week's presentation and also the RIBA lecture and annual lecture, they're now available on our website, futureplymouth2030.co.uk. This webinar is being recorded as well, so if you want to look back at Simon's presentation, it should be available live this week on our website, but we'll keep you updated on that as well. So the results of that poll is 60% lack of knowledge and results, and then shortly behind client disinterest of 20%. And just one more poll to go with Simon's presentation. What is the most important aspect of sustainable buildings? The most important aspect of sustainable building is, energy reduction, carbon emissions reduction, social impacts, health and well-being, or biodiversity. If you're viewing this webinar on the browser, you unfortunately won't be able to see these polls or vote, but if you're in the normal Zoom, you will be able to. I'm sure you guys also have lots of questions for Simon, so you can either leave it to the end for the Q&A, or please feel free to use the Q&A button at the bottom of the screen. And the results of that one, so mainly a 57% carbon emissions reduction with 21% energy reduction. So next up, we have Professor Steve Goodhew from Plymouth University. So take it away, Steve.
Good afternoon, everyone. My name's Steve Goodhew. I look after the CobBauge project at the University of Plymouth. And what I'm going to do is just share my screen for my first slide. I'm just checking with Miles. Miles, can you see that?
All good, Steve.
Great. Thank you very much. Well, welcome everyone. My talk picks up various strands that Simon's talk did, and very grateful for going after Simon for the simple reason that he's the lead author on many publications to do with that particular topic of embodied energy and carbon in general in buildings. So what we're going to do is we're going to have a little look at a project called CobBauge. And I'm just going to give you, first of all, a little bit of an insight as to where we're coming from that particular European project. I'm then going to take you through one or two elements of what the drivers were for the project, why we were actually physically doing what we're doing. And then I'm going to give you some examples of practically what we've actually done throughout the back end of the project, and give you a little bit of an idea with a poll that Miles is going to introduce towards the end. First things first, where are we? Why are we, as a project, involved with embodied energy, embodied carbon? Well, one of the big drivers for us is the use of materials that use an awful lot of energy within their production. It's quite an old topic. It's been bouncing around, but we're taking a slightly different view of it. And I'm afraid we're going to get into the stage of getting a bit myopic with graphs in a second. So I apologize for that right from now. But the first graph that we're going to have a look at is something from the IPCC, which is the Intergovernmental Panel on Climate Change, which is linked to what Simon was talking about Paris and the outcomes of that particular climate change conference. And what I'd like to have a look at in particular is this larger chart at the top. And if we hone in, this is a chart showing date along the bottom and global warming relative to back to 1850 to 1900 averages. And as you can see, that orange line in the middle is the anthropogenic warming, which has taken place since 1960. And as per Simon's graphs, it looks like we are going to be hitting approximately 1.5 degrees relative warming by approximately 2040. And one of the main drivers for this are cement emissions, and I'll show you that in a second. But if you pulled apart the predicted impacts of that global CO2, you would see that we'd be looking at all sorts of nasty things happen to us. For instance, unique and threatened systems would be under extreme stress, lots more extreme weather events, larger aggregate impacts across the globe, and large singular events such as the tropical storms and the incidence of them within the Gulf of Mexico, etc., etc. So lots of bad stuff. And one of the major sources of the drivers for these particular large impacts is actually CO2 from buildings. And this is taken from an IPCC graph, and you may be able to see the dark blue element here. And this is a Sankey diagram, which basically says that the size of the block here is in direct relation to the amount of CO2 that's being produced in this case. As you can see, buildings are on a par with transport, a little bit less than industry, but much more in agriculture. So we are, inverted commas, quite a big culprit. And one of the reasons why we're a big culprit is the amount of cement that we actually physically use. And this chart shows over time how much, as far as the relative growth and the growth of CO2 related to these particular materials, cement, iron, nitrogen, copper, silver, gold, steel, has actually happened over this period. And you can see the blobs, which are kind of an orangey red. This is cement. And you can see, especially since around the turn of the last century up to now, there's been a huge extra use of CO2, or rather of cement, which has produced considerable amounts more of CO2. One of the other problems we also have is waste, frankly, and the way we get rid of it. And you'll come clear of why I brought this in. And this is a rather hard to see graph, but please bear with me. We've got a series of countries from Austria down to Turkey here. And we're showing in blue the amount of recycling that's been going on. In yellow color in the middle, we're looking at landfill, and waste to energy is in the orange side. And every country has a different way of dealing with their waste, which is quite fair enough. But what you really want to see is more in the blue and less in the yellow. And you're probably looking for the UK. We're there. So we're kind of upper reaches of the chart being, if you're near the top, you've got more recycling. But basically, we've got a long way to go because of that landfill, about 36% is construction waste. So in essence, there's two big problems we've got there. Energy in the materials and the amount that we actually waste. And just to let you know that not all graphs are really, really appalling except for this one. I just wanted to put this one in just as a bit of light relief, just to say, I can't understand it, and I'm not sure anybody else does. So feel free to send some comments about some of the other ones that I've been putting up. So Therefore, what are we going to need to do? Well, we need to avoid the use of high energy materials like cement, except where necessary. As Simon said, there's a durability aspect to our buildings. We need to make them low maintenance as well. And we need to reduce the amount of waste that goes to landfill. So we need to really be able to build with a material that doesn't either do two of those two things. One of the opportunities that we've got is to build with a lot of natural materials, and in particular cob. Now, the reason for coming down to cob is, in particular, as far as the CobBauge project's concerned, it's a vernacular material which has been used a lot in the southwest of the UK and also in northern France. So it's a familiar material. It's a familiar type of building that you're looking at. So why not build more with this? For instance, you're looking at cob, which is a mixture of subsoil and straw built on 70mm approximately layers on top of each other and topped off with an appropriate roof. And this is the way that it would have been built a long time ago. So kind of turn of not this century, but the previous century. And the main adage was that you always needed to give it a good hat and a good pair of boots. In other words, you needed to keep the water off the top and you needed to keep the water off the bottom, because that was one of the susceptible elements to the material that would make it deteriorate. But there are many properties in and around the southwest of England and in northern France that are well over 200 years old that have been built with the material. So it is a durable material if built with property. So if you're going to build with it again, what's stopping us? Why can't we build with it now? Well, here's a property, the one on the right-hand side is actually a property in Dartington that has been built in the last 10 years and finished off. But since then, the thermal regulations, Part L of the building regulations, has become more tight. And newer buildings, such as the building you may have seen in Grand Designs, built by Kevin McCabe, which is the building on the left-hand side here, have needed to put large amounts of external insulation on them to be able to get them through the regulations. And frankly, do you need to do that? What you're looking at now is a thermographic image of a cob building that's been extended. And I'll look at this in a little bit more detail, but basically you're looking at the green and the blue temperatures, because this is the outside facade of the building, for being a touchstone of better insulation. So if you're looking at this particular building, we've got cob, which is this block here. We've then got stone. Then we've got a 1980s cavity wall, and then we've got a 1990s cavity wall. And the two areas which are performing about the same is, in fact, the 1990s cavity wall and the cob. So in essence, cob as it is, unmodified, should be able to perform just as well as a 1990s cavity wall, U value or no U value. So this thermal transmission value, however, is not right for cob. And to get through the building regulations, we're looking at approximately 0.3 watts per meter squared Kelvin if we're going to be able to adhere, or less, adhere to the regulations. And cob does not have that. The project itself, therefore, is to try and take cob and get it through the regulations. We're the lead partner within the project, and we have 3 French partners and 2 English partners beyond ourselves. That includes EBUKI, Earth Building UK and Ireland, and also Hudson Architects in Norfolk, and Anthony Hudson is a big supporter of ours, I'm very, very glad to say. So what we've done up to now is we'd looked at 20 mixes of cob, some with using soils from the French side, some from the UK side. And we'd also looked at a number of different fibers to try and look at, could we maintain the same structural properties of cob, but able to get it through the building regulations? And it would be trying to put a thermal and a structural mix together in one system. And lots of measurements were undertaken in laboratories this side of the channel and also on the French side. And I've got to say, we have some very industrious French partners. This is Francois Streif, who is the architect in one of the regional national parks, who looks after an awful lot of cob buildings in and around his area. And we found that, frankly, no, it wasn't possible. We couldn't get the structural values alongside the thermal values out of one cob mix. So what we've proposed is a dual wall, a composite wall, one which has got a very low density layer, a density here, and this is a typical U value calculation. Apologies for those people who are not that keen on numbers, but it is a very simple set of calcs here. We've got a layer here which is representing the dense cob, and we've got a layer here which is representing the lower density cob of about 340. And if you do the calculation, we can end up with using the thicknesses approximately of a normal wall of about a value of about 0.28, which is below 0.3, which is actually what the regulations require. And this is one of the prototype walls that was built in France about 2.5 years ago. And as you can see, we've used a red soil for the low density side, that's here. And we've got a yellow soil, which is used for the high density. And that was the last kickoff with all of the partners together, with representatives from both sides of the channel. So our next phase, the second phase, is looking at building, monitoring, networks and training, and to try and roll out the technology. Now we've gone through the laboratories, now you need to be able to get it to market, inverted commas. And the networks and training, well, you need these people out there that know how to use the particular material, and you also need to contact contractors that are interested, clients that are thinking of it, designers that like to use it. So one of our major raison d'etre is actually to talk to you people and see if you're interested. And we're also looking at monitoring, and over 2 heating seasons, because there is no way that only laboratory measurements are good enough really to be able to persuade people to be able to use this particular material. So one of the things that we've been using past thermal testing is, and looking at a series of results, is to take some of these frankly prototypes and build with them. And we had a choice here. This is a graph of thermal conductivity against density, and here are our insulating mixes, and here are the structural mixes, and we've picked out a couple of mixes here that we're going to start physically using to build with and to get through the building regulations. And this is the stipulation, as I mentioned before, the 0.3 that we need to go through. Now, if you were to use traditional cob, you would actually get a calculated value of approximately 0.79, which is miles above where you want it to be. And if you actually wanted to get to 0.3, you'd actually need a thickness of about 2 meters. So it really is, no, this is not going to work as far as the values that you need for the wall. And one of the rationales for not being able to use one single mix was if you chopped half of the density, you would then get approximately down to 0.29, but actually the structural properties would not be able to hold up a building. It's an insulator, so unsurprisingly, its strength is quite low. However, our dense light gives us our value that we actually physically need for our building regulations. So we've worked it through. We've done all our structural testing on our structural side. We went to Cambridge University and squashed 90 of these cores to make sure that we were getting exactly the right mix. And these managed to give us a series of results, which for one in particular of the French saws and one of the UK saws mixed with either flax or hemp, gave us a perfect series of measurements for the structural mix. And the compressive strength, whilst varying a bit, certainly we had a couple of outliers. We got some very good results with certain particular properties. And life cycle assessment, oh, look what I've just pointed out. Thanks, Simon. And there's also the BISRIA guide, which is the ICE, gives us the ability to look at the embodied energy. And unsurprisingly, the embodied energy of our particular material is very low, especially when you start comparing it with things like a masonry wall. And this is a cob wall that you can see a calculation for, which it gives a value of about, for megajoules per kilogram per meter cube squared, meter squared, 95 versus a masonry wall of 651. These are rough calculations. These, we have got Simmer Pro now that we're going to be using and doing calculations to the ISO, which is then going to give us some very, very pertinent values. And typically Simmer Pro, just to give you a very brief idea of what it does, it breaks down all those sections that Simon was talking about before and uses the ISO standard of 14040 to be able to work out what your life cycle value is using the appropriate cradle to gate or cradle to grave, etc. boundary conditions. And one of the things that we would intend to do is look at a European product declaration for the material, for which a life cycle assessment would be quite an important element. And why is this important? Well, as Simon stated, if you look at the greenhouse emissions on this graph here and time running along the axis just here, this graph shows you what happens to the amount of energy that goes into a building right from its birth. And you'll find that, this is adapted from a particular paper, that the amount of emissions in a very high energy, embodied energy building are in the very early stages of the building. Well, frankly, we've got a climate crisis now. So if you want to actually remove a lot of carbon quickly from this whole chain, it's better actually to produce with a much lower carbon footprint early on and then build up, because that gives us time. And that's frankly one of the things that we have not got. So what's happening now? Well, we've got some prototype buildings which are going to be built. And what we are now doing is we're now taking as a question of scale to build some buildings which allow us to work out, how does the detailing work? How do the foundations work with a building like this? Little tricky things. And the devil, as most architects know, is in the detail. So we've got a permission from the university to put a building up on campus. Depending on how quickly we hope to get through planning by about March next year and to be able to start work on the building. The French side have already started. This is an artist impression of the building. They're going to be putting up the prototype building near Caraton in Normandy. And this is, yeah, I know, concrete foundations, please don't shoot me, please. I didn't build that bit. But this is a typical view of the first lift going up of the wall using shuttering as we go around, and you can see it's got thermal corners to them to stop thermal bridging, for instance. And this is all that learning is going to be put into the CobBauge prototype building, which is going to be going up on the Plymouth campus. We're going to be experimenting with things like a curved wall. We're going to be looking at overhanging monopitched eaves. And also we're going to be putting up, or are putting up, and hope to be able to come back to this series of talks and broadcast live from the laboratories in the civil engineering once the COVID restrictions have lightened up a little bit, and be able to physically show you a wall being built during the actual presentation. We're also, again, as I say, looking at the details, in particular, how all this is going to work. And I must admit, Hudson Architects have been really, really helpful in this particular area, because Anthony and his team have been looking at that very carefully. And this is a couple of views of some of the types of buildings that we are emulating. This is a building that's already been built. This is not an artist impression. And this is a cob wall, which is put into, believe it or not, a reinforced concrete frame building. Yeah, I know. But it is a cob wall. It's genuine building, been put up there. And Francois was one of the main instigators of actually managing that, to get that to go up. And we're also going to be monitoring the buildings, because we need to prove to our clientele, our designers, the public in general, that they are working as far as their conductivity, also their air tightness, the air quality inside, radiant temperatures and energy use. And we're going to be using a mixture of thermographic elements. And this is that one that I promised that would pop up a little bit earlier. And as I said, here is the U value, 0.9, 0.9. This is a 1990s wall, so it should be about, I think, somewhere about 0.45. It's nowhere near it, but the cob is coming out at 0.9, just as good as a 1990s wall. And this is what we're going to end up doing with our two prototype walls in the heavy structures laboratory in the civil engineering labs in Plymouth, in W14 in the Brunel labs, where we're going to be strength testing it. And we're hoping that our local building control people are going to come along and have a look and actually physically see it taking its weight up. And lastly, we also won an award last year, the only UK project for the Regio Stars, which is part of the European funding awards. And we were rather pleased to get that. As you can see, we're rather smiley at the end. Thank you very much indeed for your time. Miles, if you want to flick that off.
Thanks so much, Steve. Really looking forward to seeing the final building, actually. And as you said, actually, we're really disappointed that, as we wanted to get you in the lab today, but we will definitely try and do that soon and see a real wall being built. It's really exciting. Just a poll to go with Steve's presentation. So relating to that, so how concerned are you about the energy that has been used to produce the materials in your home? So not at all. As long as my home is well designed and comfortable, I'm not really concerned. A bit, if we could replace some plastic materials, that'd be good. Energy efficiency is my concern. I would want a home that will be not expensive to run. I'm also concerned about the hidden energy contained in my home's materials, but I want it to be modern energy efficient, even if it costs more. Or I'd like to look into using CobBauge, if I said that right, Steve, for my next home, and willing to pay a little bit more. I think
Absolutely.
I would, definitely. Brilliant. Thank you, everyone. Thank you very much for everyone who's voted. So that's great. So most of you are concerned about the hidden energy, and also you'd look at using Steve's system. So thanks very much for that. Again, don't forget, soon you'll be able to view this webinar back online at our website, futureplymouth2030.co.uk. Even if you just want to look at Steve's graph again on the triangle and try and make sense of it, that'll be online. We also have lots of webinars coming soon as well. Don't forget that on the December the 16th, as our fourth webinar, Standards for Better Performing Buildings. So please register for that on our website. We're just finalising a few other details for future ones coming soon after that as well. And just some of the topics that are going to be covered. We're looking at skills, technology innovation, retrofitting, behaviour change, psychology and education, health and well-being, urban design in a post-COVID world, renewable energy, future housing, and changes to the planning system. So there's all sorts of topics that we want to cover in this series. At the moment, it's just number 4 on our website, but if you want to be the first to know when we put the new webinars on, just please sign up for our newsletter at the bottom of the website, and we'll let you know. So our final speaker before our Q&As this afternoon is James Robb, who's a Senior Sustainability Consultant at WSP. So James, over to you.
Thanks, Miles. I'll get my slides up now and let me know if you can't see them.
That's brilliant.
Okay, that should be all ready to go. Okay, well, thanks, everyone. Thanks for asking me to speak, firstly, and thanks everyone for attending today. So what I'm going to be talking about is basically some practical examples of some of the things that Simon and Steve have already talked through. So thanks very much to Simon and Steve for setting me up on that front. A little bit about me first, where I'm coming from. So I work in WSP's Sustainable Places team. WSP do a bit of everything to do with buildings and infrastructure, but I'm in the Sustainable Places team, and I'm based in Glasgow, but our team is all across the UK, really. London, Bristol, Manchester, Exeter as well. So there's people in my team working across the country. I'm also part of the RIAS Sustainability Working Group, and the Sustainability Committee convener for the Glasgow Institute of Architects Council. And I'm also Deputy Chair of the Construction Industry Council 2050 group, really trying to mainstream some of the topics we're going to be talking through now in this presentation. So agenda, little bit of reminder of some context. Going to talk you through terminology before we get into the thick of it. A couple of points on some embodied carbon guidance, not overlapping with what you've already heard before. A little bit on tools you might use to do this sort of analysis, and then get into some case studies once we've got set up for that. Okay, so firstly, what is the challenge? Embodied carbon is quite hard for a lot of people to visualize and to even conceptually understand. So hopefully you have a bit better idea of it after I've taken you through these slides today. The one thing we do know with some certainty is that it does need to come down. So it's something we should be acting on as building designers. What is embodied carbon? It's the carbon footprint of materials. So that's the greenhouse gases involved in creating that useful component or material for you to put in your building. Some of the big numbers here. So on the left, steel, on the right, concrete. So this is in terms of global greenhouse gas emissions. Just making steel is about 7 to 9% of everything that's causing pollution in the world, and concrete is about 8% as well. So those are pretty big numbers when you consider that's including everything, including transport, making transportation, the whole transportation system, all energy use in buildings across the world. Just making these materials is a major percentage of that total. One positive thing, I guess, is that it is moving up the agenda of business, and it did feature prominently in both the Architects Declare and Engineers Declare manifestos last year, and people like ACAN and LEDI as well starting to bring out much more guidance on how to address it. So actually, Miles, there's the first poll here. If you can bring that first question up, please. Thanks, Miles. So first poll, what proportion of a building's overall carbon footprint can be attributed to embodied carbon? What's your thoughts on that? I don't know, Miles, if you're able to show the results in a minute or so. Great, thanks. So most people are saying it's about half of the impact. Next favorite was between 50% and 80%. And some of you putting in those lower figures, 5 to 20 and 20 to 30 as well. So who was right? These are the numbers for different types of buildings. So generally what we find is that office buildings, embodied proportion of the total carbon footprint can be about 35%, warehouses, it's getting on for 50%, and residential as well, it's hovering around 50% for those. So those of you who selected that band were right. Maybe a lot more than some of you were thinking. Now, terminology, before I go any further. So I just want to run through these terms, which you may have come across before, and just make sure we all understand them before I go any further. So carbon, if we're talking about carbon, then what we're really talking about is carbon emissions, which is in effect greenhouse gas emissions. So we're talking about carbon footprint. We're talking about that, climate change causing emissions, and the unit we measure that in is usually TCO2e, which is tons of carbon dioxide equivalent. And the E, the equivalent, is quite important to understand, because we say carbon as the term, but it's actually a catch-all for lots of different gases within there. We just use carbon as the kind of measurement scale, because it's the most prolific of the greenhouse gases. The other gases, such as methane, are orders of magnitude much more climate damaging. So by saying carbon, we're capturing all of those different gases in one unit of measurement, just for simplicity's sake. Embodied carbon, what do we mean by that? So it's the carbon expended in creating a material or component. So if it's a brick, it's the quarrying of the clay, taking that somewhere and burning it somewhere to a manufacturing facility to be heated into a useful product, and then all of those impacts, the transport and the quarrying and the energy used for the heating of that is included in that embodied carbon footprint. Operational carbon is the operational emissions expended if it's a building, so the energy you're using, the gas you're using in the building, and it can also incorporate the kind of maintenance impacts that are ongoing over a building's life. So if your carpets wear out every 15 years, then you'd measure that as it could be said that's operational impact. It also has some embodied impact as well. Lifecycle analysis, top right. So the acronym is LCA, and what we mean by that is analysis of a building or product across its whole life cycle. So typically for buildings in the UK, we use 60 years as the lifespan of a building when we're doing LCA analysis. Lifecycle costing, a very similar term. Acronym is LCC, and these can be mixed up. LCC is not about rating climate change impacts or carbon impacts. It's about the life cycle costs across the building's life. So in LCA, you may measure the impact of a brick. In LCC, you might measure the impact of a brick against a different cladding option for a building, say render, and you would assess the costs to the client over that 60-year lifespan of those two different methods, in order to show the kind of the total cost effectively over the lifespan, rather than just having that capex expenditure up front, and you think it's saving you money, but if it wears out in half the time of another material, then you're not saving any money. This term, whole building life cycle analysis, so obviously that's an expansion of LCA, and it's really to show that the LCA you're carrying out is on an entire building, because an LCA could be on anything. Like I said, it could be a product, it could be your computer you're looking at this presentation on, or it could be a building. So correctly, we'd use this term to say we're rating a whole building. And the two terms at the bottom, so whole life carbon, as Simon said earlier on, it's that measure of carbon across the whole life of a building. And environmental product declarations, which have been mentioned a couple of times already, that is a certification that a product manufacturer has carried out and verified by a third party, declaring all of the environmental impacts of their products. And that's what we are increasingly reliant on in order to carry out LCA analysis, because we build up a portfolio of the products used in the building and use that to power the whole building analysis and get our overall carbon numbers. I won't reiterate all the previous guidance we've been through. Just one I wanted to mention really that hasn't been mentioned is the RIBA 2030 Climate Challenge document, which released in the past year, kind of setting out benchmarks for operational embodied and water use. And this is the RIBA setting out their path to a net zero future for buildings. So what is one thing to say about this is that it's almost the first time we've had a document setting out targets for embodied carbon across industry. So, you know, before this came out, and the LETI climate designing for climate emergency document as well acted on this as well. So before these documents came about, we didn't really have a reliable target to be aiming for when we're doing these assessments. So it's really good that they have now come out and there's something to measure against. There's another discussion as to whether these go far enough or if they're sufficiently robust, but at least we've got something now to measure things against, and we know how we're performing. Next section is on software and tools. So some of the tools you might use to carry out whole building life cycle analysis are in this list. The top two, eTool and One-Click LCA, are in green because those are the only two commercially available tools that are currently approved for use under things like BREEAM. BRE Impact can also be used as for BREEAM, but it's not as detailed a tool as these top two. So I'm using these two at the moment. Other tools that are out there that you may have heard of. So HBERT is a tool by Hawkins Brown Architects, which is a Revit plugin, which is free to download if you want to have a play around with that and you use Revit. The Rail Carbon tool is something Network Rail set up a number of years ago for rail projects, and these are the tools are also around. So Ecolab, similarly developed by architectural firm. EC3 is actually open source, so you can use this one free of charge, though most of the data seems to be North American at the moment, so maybe it's not useful for the people on the call, but useful to have a play around with anyway. And Tally as well. Some of my US colleagues are using that a lot at the moment and seem to be well, I was going to say enjoying it. They seem to get good results from it and think it's a thorough tool. And okay, let's get into some case studies then. So, well, actually, before case studies, this is the process, my process wheel for doing whole building life cycle analysis. So 6 stages, quite simple. Number 1, develop a baseline carbon footprint for your building based on materials types and quantities at an early stage, say concept stage, Reba stage 2. And the RICS professional statement on whole life carbon calculation for the built environment helps with that, because it determines certain things you can assume at an early stage of the design. So if you're not at a point where you know that certain materials are defined, there's guidance on what materials you should assume for that baseline, and there's also guidance on transport distances that should be assumed for various materials at that early stage, which enables you to calculate a baseline. Step 2 is to analyze that baseline and determine the carbon hotspots in the design. And the carbon hotspots are basically where the most carbon is in the project. So that could be in terms of which stage of the project the most carbon is being expended, whether it's in the construction phase or the in-use phase, for example. And you can also determine those materials that are causing the most carbon. Third step is to really act on those hotspots and propose reduction opportunities against them to try and get carbon footprint down. 4, establishing a carbon reduction target. So, for example, some clients I'm working with have a target of cutting that baseline figure by 50%. That's the most stringent target I've seen on any project. So other projects I've seen, actually, we've done once we've analysed stage 3 and assessed some sort of feasible carbon reduction opportunities, we've set a target based on those feasible solutions. So it can be done. It's up to the team to decide what to do. Step 5, refining these opportunities with the design team and just really trying to embed them into the design by the point you get to stage 6, when you're at sort of end of Reba stage 4, I guess, steel design, and you maybe as a point in your contractor, so you want to have those opportunities embedded in the design. Before that happens, obviously it gets more costly to change things as you go on, and you want them to be embedded in the tender information. Okay, so very briefly, first case study is on rail stations that I've been working on in the past couple of years, and it's just to show the importance of embodied carbon in this instance. The next case study will be on some a particular case study in southwest England, closer where you are in Plymouth, so that'll be very applicable for you. But firstly, just to set up this kind of scale of embodied. So I'm involved in the new build stations for the HS2 line. This one in that's the wrong title actually, but this one's actually in Birmingham Curzon Street Station, and that's an internal shot of it. So very large stations, effectively sort of 16 platform super stations, as they call them. And this is the one on the outskirts of London, Old Oak Common, and I'm involved in the London Euston extension as well, doing the carbon management for those kind of very large projects. And next poll question here, actually, Miles, if you can bring it up, thank you. So for these railway stations, which life cycle stages are responsible for the most greenhouse gas emissions over their whole life? So if you can have a stab at what you think the biggest impact would be before we proceed. Now, it's over 120 years because that's a sort of standard lifetime assumption used in the rail industry, which is normally for the bits of infrastructure, but they apply it to their stations as well. So we're assessing them over 120 years in this case. Thanks for that, Miles. So the results are, most of you think it's that choice of construction material. Well, half of you think that, and almost a quarter of you think construction process, and other quarter operational impact. So yeah, most of you think in construction, but a good spread across those 3 impacts. So if I can flip on to the next slide. What we've found for these stations in terms of the carbon hotspots, firstly, the life cycle stages. So you can see here the biggest chunk of the pie, 66%, relates to that choice of construction material, which we refer to as stages A1 to A3 in the life cycle module chart. So half of you are right that that choice of material is responsible for the most in this instance on this station. Some of you said that energy use. In this case, actually, energy use was only 7% of that overall impact, so much less than the construction material. And I'll explain why in a second. So, and construction process was the other big choice that you made, which was the second largest impact for this building. Now that I say for this building in particular, so because perhaps unfairly, you can't see the kind of huge underground box that runs underneath this station. So there's sort of a 3-story high concrete, concrete box, effectively, 1.5 meter thick concrete diaphragm walls going down 3 stories because the station platforms are all at a very low level. So For this building in particular, it's perhaps not surprising that the construction materials were the biggest, just because there's that vast amount of concrete going into it. So that's one reason why energy use is smaller than you might expect, and than you might see in other buildings. But also the factor here is that over 120 years, if you follow the decarbonisation figures for UK grid electric, by 2030, we're really expecting grid electric to actually be a low carbon source of electricity because of the continued reduction in the amount of coal in the grid and continued increase in renewables and nuclear in place of coal. The grid is becoming much lower carbon source. So this building is all electric. There's no gas in it, so it's really taking advantage of that future low carbon energy that we're expecting to see. So that assumptions built into here, which is it's a reasonable assumption based on the trajectory of decarbonisation as we've seen it over the past 10 years. Materials hotspots. So this is sort of diving into this proportion of the overall impact and just showing you the materials. And I've shown you now. So I think I might have had a poll question about this one as well, but we'll press on. So yeah, okay, too late. We'll skip past that. I was going to ask you to guess which of these had the most impact. But as you can see, in this project, the cement has the most impact, followed by steel rebar, followed by aggregate. So 3 of the largest chunks of carbon are the constituent parts of the reinforced concrete. So I'm not giving you any marks for your answers on that one, I'm afraid. But yeah, as you can see, the reinforced concrete effectively is the materials carbon hotspot, and within that, the cement is the major component. What I've had comments previously is, why isn't the glass bigger impact? Most of the external walls are glass, and yes, it does have an impact. So it is showing up in here as one of the hotspots, but it's much less impact than the concrete. On the one hand, because there's so much concrete in there, but on the other hand, because of that carbon intensity of the making the cement, it inflates maybe this part of the pie chart. So that's what's happening on those rail projects. So next case study, looking at projects that are taking action now on this in Southwest England, and one in particular is one I've been working on with Stride Treglone in Penzance Creative Cluster. So this is a commercial development for creative businesses in Penzance. So initiative of Cornwall Council, and it's a sort of 3-story on the in the town centre there. A lot of glass, obviously structural frame of steel to hold it up, and retained section of existing stone wall along here, which is quite interesting. And I'm going to run you through now what we have found on this project. So similarly to the railway station I showed you, most of the impact on this project seems to be coming from the, coming from the materials. So that A1 to A3 stage, that choice of material was the biggest, responsible for the most carbon. So that's the second is the B impacts here, which is replacement of material over that life of the building. So in this building, for example, facade will be expected to last maybe 35 years. So in the 60-year life, you'd be expected to replace at least some of it in that time. And internal finishes, so carbon, vinyl, paint will all need redone over that life, maybe 2 or 3 times. So you see the impact of those materials being replaced in here as well. But yeah, bigger than the construction process itself, which comes out relatively less in terms of carbon. Materials carbon hotspots in this one. So metals in this case are biggest. Steel, that includes the steel frame and steel, it's a composite floor, so it's the steel in the floor, and then that will also include the reinforcement in the concrete as well in this case. Secondly was the concrete, so substructure floor slabs, and then glass was coming out next. Obviously the facade is very glazed on this one, so glass coming out there as a hotspot as well. Now, I suppose why the team are doing this is because Cornwall Council have a requirement for their buildings to meet BREEAM Excellent. So this analysis is done under BREEAM New Construction 2018, and so the way we've done the analysis is to satisfy that. The first bit of the analysis, the first requirement under BREEAM is to do that baselining and hotspotting exercise that I've just displayed. The next part is to look in more detail at some aspects of the design. So there's a requirement to analyze the superstructure and some options around that. So that's what we're showing here, that we rated these 4 options. So this option here, also this is the sort of code language you're required to use doing BREEAM. So this column is the baseline steel frame option. We then assess that against a concrete frame option and a timber frame option, so mass timber approach. And also we reviewed leaving the frame as it is and just changing the window spec from aluminium, the aluminium double glazed units, but we changed it to a composite aluminium timber window frame. So you can see clearly that every option we assessed would result in less total carbon footprint than the pure steel frame option. Concrete option would result in less carbon overall. The timber frame option here obviously showed the biggest carbon reductions. This one just getting rid of that amount of aluminium in the design and the building looking identical externally, just replacing that with the composite system. So it looks timber internally and looks like aluminium externally. That did save a good chunk of carbon as well. And yeah, I guess a bit more detail on this from this was a different office building actually, but it's a very similar study of comparing different framing options against each other to work out where you may save some carbon. So in this instance, we reviewed a CLT steel hybrid design, which was a steel frame, but with a cross-laminated timber floor slab. Composite deck slab was this option, so steel frame with a concrete and steel composite floor. And this option was the complete reinforced concrete frame. And that was really to work out where the efficiencies lay. I mean, overall, as you'd imagine, the timber did come out as lower in carbon. But the fact that you've still got a steel frame in this case limited your ability to sort of drastically cut the overall carbon as much as I would have liked. So it was about 1,000 tons less carbon to change the floor slab, but not as much of a saving as if you'd managed to get to a full mass timber structure altogether. One complication there was that this steel and composite design is actually quite efficient and they act in action together. So the floor slab helps to stiffen the steel frame, and you lose that benefit going to CLT, so the steel ended up being a bit more. But broadly, without getting into too much detail, you can get the timber option to save carbon. and you save more carbon the less steel you end up with. There's also the cross benefit of this option was shown to need less deliveries to site because you can get more CLT in a lorry than you can concrete and rebar, and so less traffic going to site, so that's a knock-on benefit. And also the other thing to mention is the carbon sequestration value of using timber. So that carbon that's locked up in the timber as trees grow, effectively, if you take that into account, that's a much bigger carbon saving. Don't normally include that in formal LCA measurement, just because of the complications of the standards, but it's a side benefit, I guess, of using more timber or more bio-based materials. So next bit of analysis that you do under BREEAM is to try and do some substructure options. And so in discussion with the structural engineers for this project, which were MBA Truro, they had a few ideas around some substructure options. And I mean, unfortunately, we're sort of restricted by the ground conditions, as you may be in other sites as well. So we didn't show much of a benefit of these different options. What we try to do is analyze whether they can move to a more precast, use a more precast concrete, which you might be able to reduce the slab depth and save volumes of concrete. And we're trying to get away from using as much steel in the piling as well. They had a sort of a steel cord pile initially, which is coming out quite high, but actually found after further ground investigation we could move away from that and save carbon. So really on this example of substructure analysis, we were trying to analyze those different sort of conceptual approaches to the design before you get to the point of specifying the concrete mix. So make those savings by reducing quantities effectively first before getting into the spec. This slide is showing getting into the spec. So this is on a different building again, the Featherstone building in central London, where we were able to, once the design was set in this case, look at different concrete elements of the design and work out what we could do with the concrete mix to get the carbon down. And as I said in the carbon hotspots, so the cement in concrete is the biggest carbon hotspot. That's because it's so carbon intensive to make, the heat required to make it. So reducing the quantity of cement in your concrete mix is the major way to cut its carbon footprint. So in this building, for example, pile caps, the structural engineers, which were HTS on this project, structural engineers managed to design pile caps with 70% cement replacement, and they were happy that there was time in the program that they could do that. So yeah, the more cement replacement you use, generally it takes a bit longer to go off the concrete. So you've got to be in your build program to allow you to do that. The concrete superstructure elements like these columns, they reckoned 50% cement replacement was feasible to get the build program to work. So not as high as the substructure, but that was more to do with the construction methodology. And this element you can see here is the core, so of the lifts in there and the staircases. And I mean, on the one hand, interestingly, on the other hand, disappointingly, they didn't do much cement replacement in there. What they did do is put silica fume in there. So what you tend to use in most buildings at the minute is use GGBS in place of cement. Previously you may have used PFA, but there doesn't seem to be much of that around these days. So GGBS is the go-to for cement replacement at the minute. But for this core, they used silica fume, quite a minor replacement, and they didn't put any GGBS in. And the reason there was aesthetics. So there was going to be an exposed concrete core, and the architects were quite keen on the shade of concrete with no cement replacement in it. I'm not sure why, but generally the more cement replacement you put in, the lighter the concrete becomes. So if they wanted to particular dark shade of grey, I guess they wouldn't accept any replacement. So yeah, unfortunately we couldn't do any replacement there apart from this mild silica fume, which cut the carbon slightly, but not really much to write home about on that particular element. But yeah, a lot more success in the hidden elements here. Yeah, another example of substructure. So as Simon mentioned, really, reusing buildings is the best way to cut carbon, not building new ones. This obviously is a new building, 22 Bishopsgate in London. But one positive thing of this building to mention is the team reused the existing foundations that were on the site. So another building was removed to build this larger building. But you can see only the red piles here were the new ones that needed. All the others were, I think there was 2 previous sets of substructure on this site already. So they were able to design their substructure and ground floor slab and basement slab loadings to utilize that existing structure. So much less new concrete was needed, and they took the benefit of that existing resource in the ground to reduce the concrete quantities they needed to build this tower. So yeah, that's one example of where the team put a lot more effort in the design stage to incorporate the existing. Okay, they didn't retain the whole existing building, but they managed to retain one of the biggest carbon hotspots of the design, the substructure and all that concrete and steel. Lastly, I want to go through, well, yeah, so hard landscaping is another requirement of BREEAM to rate. So this is showing us rating concrete versus clay versus stone for the hard landscaping elements around this site. And there wasn't much in it, to be honest, in the overall scheme of things, probably because the external areas are limited. But there was a benefit in going to clay or stone rather than concrete in this analysis. So we'd be encouraging the team to consider that in the future, or perhaps source a lower carbon precast concrete if possible. Okay, so those are the studies I'm going to go through today. This is them all shown on one chart. So number 1 on the left here was our baseline. Number 2 is showing that saving you would get by adopting low carbon concrete for the substructure, so the foundations and the ground floor slab, which is about a 10% cut overall. Third option is looking into the insulation spec. So the insulation on this building was a mix of mineral wool and PIR, and we compared whether you could get rid of all the PIR and just go purely mineral wool. We found it was quite a modest saving, 1.5%, and that is because there's so little PIR really in the project. They're using PIR to cut the wall depth down. So if they moved to rock wool in those particular locations, the wall thickness would probably impact on the internal spaces too much at the stage of the job that they'd got to when we reviewed that insulation option. So we decided not to proceed with the swapping out the PIR. What I would say is that the rock wool is much less embodied carbon than any oil-based insulation like PIR or XPS. So if you can only use rock wool or mineral wool, that would be much preferred generally. If you can get that allowance in the wall thickness into the design early enough. Next one is showing the timber frames. So just changing that timber for the window spec from purely aluminium to a timber aluminium hybrid looked like it could save about 15% of the project overall. So that's a good saving that the team are trying to work out at the minute on the cost team or costing to make sure we can get it built in. Option 5 is showing that concrete frame comparison. So if we'd moved away from steel to concrete, it looked like it was going to reduce the footprint by about 20%. So yeah, that's something, keep saying concrete's high carbon, but in some instances, when you're rating it against other materials, you may end up with a lower carbon solution. And that's because steel is so carbon intensive as well. And the last option here is showing a 30% reduction if we could have adopted mass timber throughout. Now there's some discussions ongoing about that and complications about securing the supply chain. So that one's probably less likely to happen than the windows or the concrete at this moment in time. I should have said the project's in the middle of planning at the minute, so it isn't a complete project. Okay, just to finish off very briefly, a couple of slides. What next? So hopefully we're heading towards net zero carbon, and I've just talked through a few case studies of some projects that are looking at addressing the embodied side of that. You know, industry's made great strides in cutting operational emissions in the last 15 years, perhaps, to the point where embodied is becoming now much more important as a part of the bigger picture, and projects are addressing it now, but it's not completely mainstream. So just to wrap up my talk, I mean, hopefully we're now on the pathway away from this peak of emissions, and we're seeing some instances of good things happening at a project level anyway, and you know, things on the global scale like China's net zero announcement, net zero 2060, and probably USA coming back into the Paris Agreement. That's all good signs. We keep hearing more and more about UK grid going without coal, so that's expected to increase, as I mentioned about decarbonisation of the electric grid. Expect that to keep increasing, and we keep seeing more and more examples of sort of records being smashed for tallest timber structure buildings. So for example, this is one from last year, 18-story timber structure. This one's in Norway, and it's really good from my perspective to see these records being broken. It means we're carrying on building in these, well, they're not new materials, are they? Lower carbon materials, new old materials. And one more example of timber frame building that I like. This one's in Australia. So, you know, Europe, around the world, we're seeing good examples now of these approaches to design. And I guess it's a case of my wish that we're just going to see this becoming more mainstream now. And that's what I'm pushing for in my work with the CIC as well. And that, I think, is it from me. Oh, a couple of rules of thumb from me on reducing embodied carbon. All of these are good ideas to bear in mind. This is the Australian office again. This picture is of a building in Denmark by Lendiger Architects that I really want to go and see once we get some travel restrictions lifted, because I believe it's finished now. It's an apartment block built out of reused brick panels from a Carlsberg factory. So the Carlsberg factory was being dismantled, and the team managed to get them to cut it up into panels so they could then build their new facade for this apartment block out of it. And they've done this sort of patchwork affair. So yeah, looking forward to see that one. And yeah, I mentioned carbon sequestration. Steve's talked about his CobBauge project. That's a great thing. I'd love to see that getting used in some projects. If you can get that approved, Steve. This is some of my colleagues helping with a straw bale build, community building last year in Brixton. Sorry, Tulse Hill, next door to Brixton. So community building, which was uber low carbon, you know, straw bale, timber frame. Really nice to get involved with that one. And that's it for me. Thank you very much. I'll stop.
Thank you very much, James. Brilliant presentation. Thank you very much. Now it's time for your questions, Q&A. Please, we have some people that would like to ask some questions, but please raise your hand now if you would like to ask any of the panelists some questions. Whilst you're doing that, I just want to say a big thank you to our lead partners. Without these guys, this webinar series wouldn't be possible. So thank you very much to Plymouth City Council, the University of Plymouth, the European Union Development Fund, Her Majesty's Government, the RIBA, Building Plymouth, Constructing Excellence Plymouth Club, and Strides Cologne. Thank you very much for partnering with us. It's much appreciated. We have some questions. I'd like to go to Christopher, because there's a good question that's come in the Q&A. If you'd like to ask a question, Chris.
Yeah, hi Miles, can you hear me?
Yes.
Cool, yeah, thanks for that. So a question for James really, or anyone else. I was just wondering that apart from the last couple you touched on, the case studies you showed mainly contain concrete and cement, and I was just wondering, why are we still using this when we know its negative impact? Surely we need bold leadership to address this sort of elephant in the room and move away from using this entirely and do this immediately. So are there any examples of sort of mainstream commercial large scale examples of this happening, and can you give us an insight whether this is being discussed within the industry?
Thanks, Chris. Would anyone like to answer that one?
Yeah, I mean, thanks, Chris. I mean, yeah, I think you know, steel and concrete are definitely still in everyone's minds in mainstream construction industry as the first go-to materials. But I try to show you some examples of where, from a structural framing perspective, moving to mass timber, for example, seems to be growing in popularity. It's not fully mainstream yet, but we've got enough good case studies of it now that it's being discussed at a serious level. And I'd say, you know, for foundations, probably it's difficult to get away from concrete, and I haven't seen any. Well, there's some things like limecrete, which I've seen used on a smaller scale, but nothing at sort of a commercial building level yet. But yeah, on the structural framing, I'd say moving towards mass timber seems to be a trend that we'd like to see continue.
Thanks, Jane. Would anyone else like to comment? Simon.
Yeah, I mean, I think the there are a lot of solutions out there, but I think the problem is that industry and certainly client bodies are not taking them up fast enough. And that may be partially to do with regulation and partly just to do with education and inertia. But I don't believe there's any real excuse because, as I say, the examples are out there. They don't necessarily cost, as I try to show, they frequently cost less or equal to the standard solutions. And I think it's beholden to architects to advise much more clearly on this. It'll happen, but it'll take time. But I think we need a bit of urgency in the whole process to get things moving along.
And I would just add one more thing, that we're only really getting to the point now where embodied carbon is becoming legislated. So, local authorities are starting to request it be measured for the first time now. The new GLA London plan, for example, is asking that now. I mentioned seen so much good work on operational carbon in the last 15 years. That's because legislation has pushed that, and we're just getting to that point now, maybe where last couple of years we've had that extra push, I guess, from my perspective.
I think there's a clear business case for doing this. And I think waiting for sort of local authority legislation is not really good enough for me. I think it's
I agree. Yeah.
Yeah, absolutely. If I could add to the fact that I discussed with one of the architects that was working with the new CobBauge building, and he was concerned about using earth for the first time in his practice. So he checked on his PI insurance, and basically the professional indemnity insurance said, no, we're fine, we're going to cover you with whatever material you physically use. You just got to do your part of the process correctly as a designer, which we trust you to do. But there are actually no limitations. So if you wanted to start scoping using Gambians as a form of foundation or other materials, but as I hinted in my presentation, and I think as James and Simon have hinted it as well, it's using materials where they're needed rather than ubiquitously using them out of habit or because there's a perceived risk.
Thanks, guys. Is that okay, Chris? Would you like to come back at all? He's gone. We have another one from Greg, Greg Slater, if you're there. Hi, Greg, can you hear us?
Yeah, hi there. This is a question for James, and it's taking you back to the Penzance building, which I know well from my former team colleagues in the council, now with Treveth Development here in Cornwall. We've been looking at this whole sort of decision-making process for structure down here, and your presentation prompted a couple of thoughts. The first was around the frame, and completely get the sort of consideration of timber, but just wanted to raise the question around the fact that we pretty much all, if not all, timber for frame use in Cornwall comes from Scandinavia. So just wanted to ask about whether the transportation was factored into your consideration of timber use. And then in terms of the concrete, we've got a fairly unique set of circumstances here where with the China clay industry, we've got a lot of secondary aggregate, and there's a precast manufacturer here that does a lot of work across the country actually that uses that secondary aggregate. We also have block manufacturers who are literally locating their plant right next to the clay extraction. So they are able to use that secondary aggregate, pretty much direct from the pit, and the blocks are air cured. They can have GGBS to displace some of the cement as well. So it sort of puts us here in a position where we kind of have to look at concrete maybe a bit more seriously and its use than we might in other areas. So just really a bit of that local nuance around those two elements and whether that's been factored into your thinking.
Yep. Thanks, Greg. And yeah, that's one aspect I found quite interesting to learn about when I started working on that project. Your industry you've got down there in terms of secondary aggregate in particular was showing some good environmental benefits over maybe more UK average environmental performance. So I suppose firstly on the timber. So yes, the transportation impacts are taken into account, and when you look into the analysis, I suppose more people are more used to thinking about food miles maybe, and you think, well, if you're getting strawberries from Spain, it's probably not as good as if you could grow them down the road in England. But generally, we find that the transport impacts are much less important in total carbon than that choice of material in the first place. So you can find that bringing something higher carbon from further away is actually still carbon efficient, depending on the material. Example of that was a review we did of Welsh slate versus China slate, which the results showed that it was better to source it from China and get it shipped across to our site. But yeah, so I mean, timber to Cornwall, transport impacts are taken into account there. And although they are an impact, they're much less important than the actual A1 to A3 impact of that steel. And on the aggregate, what I tried to mention was that the biggest carbon hotspot in the concrete is the cement, and the aggregate and the sands and the water tend to be much lower consequence. They are of consequence, but replacing the cement is the way to really cut the overall footprint drastically. So that's what we'll focus on. And so yeah, you've got great secondary aggregate source in Cornwall, which is great to cut the aggregate's impact. But the bigger opportunity is in that getting that cement content down, and having that source of GGBS to cut that. So hopefully that covers your points, Greg.
Am I still? Yes, thank you. Just a couple of points off the back of that. Firstly, you've reassured me because we have switched our home designs to timber frame, and also just an interesting one that might be worth going back to have a look at if you're looking for some interesting alternatives for substructure in a former life, I was the client lead for the delivery of the Green Build Hub at the Eden project, and the slab there, the substructure beneath that was actually tyre bales, so helping get rid of some of the mountain of tyres, and the reduced size slab above that did have cement displacement in it as well, which again was produced by a very local manufacturer to the site in the China Clay area.
That's interesting.
That one's performing.
Yeah, I can remember those bales sitting in the car park next to the Green Hub for quite a while before they were hoisted in, weren't they, Greg?
They were, yes. Yeah. It took a while to get Gilbert and Good to agree to give it a go. It's still serving its purpose well now as a learning resource centre for Eden Project Learning. So yeah, it's in use.
Great stuff. One more point actually on timber. So yeah, most like mass timber is sourced from Europe currently in the UK, but there is a similar consortium, maybe to the one Steve's involved in, but focused on UK mass timber production that I've had some contact with, which is run up here in Scotland by Edinburgh Napier Uni, who've just secured some funding. So hopefully within a year or so, there'll be some UK CLT being produced. So that'll cut your transport impacts even further, Greg, and you can have even lower houses, carbon houses. Look forward to seeing that.
Brilliant. Thank you very much, Greg. If you please keep raising your hands if you want to ask a question. We've got a bit more time left. I thought we had a good one in the chat actually for you, Steve. I don't know if anyone saw from Chris Roots. Has any fire testing been done on the hybrid cob wall? I thought it was quite an interesting question.
Yeah, absolutely, and it's one of the kind of next stages along in the properties and the areas of which we're going to be looking at measurements to move on to production is concerned. Our first goal was obviously to get through the thermal regs, so that's what we've been concentrating on. So it's thermal and structural first, part A and part L. Part B, of course, kind of rings true, and you need to get through that element as well. We're going to be doing some tests to the ISO, but some of the smaller tests, not the sorts of tests that the BBA would be undertaking, which are extremely expensive and very difficult to set up, and certainly we don't have the capabilities of doing that within the university. But we're intending to come up with an approximate rating in minutes for the appropriate 600 mil wall that we're looking at. We may end up doing a scaled version for the simple reason just fitting things into spaces to be able to do it. But I know that the straw bale lobby did something very similar, and they did a practical test with a lime rendered on both sides straw bale, and it lasted 2 hours, and actually filmed it. And there's nothing like a piece of film and a visual representation of something to persuade people that actually there's nothing wrong with this. And luckily, or unluckily, I suppose, I was asked in several instances to go to some COB buildings that have been involved in fires. And the damage that was done was very, very limited by the fire. However, the COB walls had to take a long time to dry out due to the very zealous fire brigade, which you can imagine. And also the ignition point was unsurprisingly thatch, not anything to do with COB walls. So in essence, yes, they survive fire, no problem. But after extinguishment, they do need a little bit of settling.
Brilliant. Thanks, Steve. We've got a question from Sarah Lee. Sarah, are you there? Sarah is actually our chief organizer for this project as well. She's one of our members of the team.
Oh yeah, sorry, you caught me on the hot multitasking. Yeah, hang on. I was just in the kitchen. Hang on. Hiya. So my question was really to James. It was about the use of CLT. It's obviously something that we've been looking into as a commercial practice, but do you find that commercial clients are a bit afraid to use it, obviously in the light of Grenfell and fire combustibility?
Well, my answer would be no, because I think there is an issue that when the CLT is used, though, you need to also take into account the acoustic layer that has to be put on top, which is cement, either cementitious board or poured cement. So that needs to be factored into any assessment. But I'm working with various clients who don't seem to be concerned. Their concern is to make sure that it achieves the performance that they need in all respects, and that includes the fire rating and so on. I mean, oddly enough, timber actually burns better, is a better performer in fire than steel, without, obviously steel if it has, without, because you'll retain its structural integrity, whereas steel just becomes like spaghetti. No, I haven't found a problem. I don't know whether James has, but
yeah, I mean, I agree with what Simon said. I'd say that probably, yes, they're nervous, but once it's explained the technical performance of timber, that as Simon says, you know, timber chars and therefore is fireproof for longer than a steel structure. The sort of assumptions, isn't there, about what you're used to using, and if they're used to seeing a steel frame, you think, oh, timber burns, so that you can't possibly use that. But once it's actually explained of the technical properties of it and how it performs in fire, then once those risks are the performance is explained, then you can get around it. So I'm working with a client at the minute on who are interested. They have a lot of warehouses. They're building warehouses all the time, distribution centers, and they're hoping to move away from a steel structure for those and adopt a glulam portal frame for that. And yeah, their first worry was it can't possibly perform in fire, but when you get the right people in the room who know how it performs and how to design with it, then yeah, you can work it out.
Thank you. It seems like an obvious solution to me, just for relatively low-rise development, which we have across a lot of our cities. Yeah, I'll be looking into it, and we'll be looking to include that on this programme as well. I've got some engineers lined up to talk to us, so watch this space.
Well, in the UK, people have built up to 8 to 10 stories in timber frame and CLT, but the architects SOM, Skid Moorings and Merrill, they retro-engineered one of their projects in Detroit, which was a 50-story residential tower, and they showed that it could be built from a timber frame structure. The only thing they had to do was the junctions at where the columns and beams met had to be concrete or steel, but all the vertical structure, including the shear construction, could all be timber. So it is remarkable. If you start to think differently, you can make these things happen.
Thanks, Simon. And I'm afraid that is all we've got time for today on the webinar. Please join us for our next one on the 16th of December, Standards for Better Performing Buildings. You can sign up on our website, www.futureplymouth2030.co.uk, and also keep a lookout for other webinars which will be coming soon on our website too. And also don't forget that you can still view this back this week. We'll be putting this on our website to view back as well. Thank you so much to Professor Steve Goodhew, James Robb and Simon Sturgis for their time this afternoon. And I really hope you enjoyed it. I hope you have a really excellent rest of your week. And thank you very much. Bye-bye.